suppose that you are going to flip a coin 4 times and record the results. What is going to be, hey, chill out. What do you think is more likely to happen? Getting either 4 heads or no tails in a row, or getting 2 heads and 2 tails in any order? And like, why do you think so? All right, just jot down your ideas. There's no right or wrong answers except for the ones that I say are right and wrong. You're just like making a prediction. It doesn't have to be a right or wrong. Just write some stuff down. I was just being funny about the right and wrong answers. This is not for a grade. This is just for brain exercise and trying to put your thoughts on paper. You're doing great. Look at all these pencils moving. Yeah. A what?
A 50-50 chance. So
Yeah.
half of it will be heads and half of it will be tails.
I like it. Anybody else? All right, well, let's see. All right, we are going to be doing some coin flipping. Now, I need the coin flipping to happen on the carpet. Because, like, on the desks, it's really loud. And, like, I'm an old lady and my nerves are shattered. Yep. I can't handle it clicking on the desk. It drives me crazy. So, you are going to conduct an experiment where you are flipping a coin 4 times and you are tracking the results. So you are going to perform 10 trials of 4 coin flips. Okay? So you're going to put like H, T, T, H, whatever you get. So each of these should have 4 flips. Okay? So you're going to do a total of how many flips? 4 times is 40. Does everybody understand how to do the experiment? So if you're working with a partner, one of you can record and one of you can flip. If you're working by yourself, you're gonna be busy with both hands. Okay? All right, we're ready? All right, go.
Sorry.
Don't worry about filling out the number of heads yet. I'll show you how I want you to do that, okay? Right now you're just writing the T's and the H's in the middle column. I'm going to turn these into our number of heads. So we're just counting heads. We're not counting tails right now. So here I just have 2 heads and then 1 head, 2, I was really heavy on the tails, wasn't I? We're going to translate this into a frequency. So, for example, how many times did I get 0 heads? Only once. How many times did I get 1 head? 3. How many times did I get 2 heads? 6? Sorry, I doubted you. It is 6. How many times did I get 3 heads? 0. And 4 heads? 0. Okay. Oh, yeah. That's a good way to make sure that you did it right. Okay, so everybody got the number of heads column and the frequency? Okay, here's our... All right. So mine was 13600. Okay, so can we go around the room? What did you guys get?
00451.
00451. Okay, next.
Hey, what are the last 2 of yours? 0, 0.
Huh?
Oh, I was just doing the first one.
Okay, who's next?
Oh wait, I put my own. 1, 1, 2, 4, 1.
1, 1, 2, 4, 1.
Oh,
Okay, next. 24220. Okay. Next.
02530.
Ooh, that was very symmetric. Good job. All right. Next.
03340.
03340. That was pretty symmetric too. All right, next. 3610. Okay, next.
Oh, shit. 11440.
141. What? I think you might be missing some.
11440.
440. Sorry, that's my fault. That was me missing some, not you. Did I get everybody? Am I missing anybody?
I got one.
Okay.
03610.
Are you in the same group as this one, or did you just get the same thing as them? Okay, well that's exciting. Anybody else? What?
I think there's more.
1, 2, 4, 3, 0. Am I missing anybody?
13540.
3, 5, 1, 0. Okay, I got room for one more. I think they went like right after me. Cooper, what'd you get? 0, 5, 3, 2, 0. Okay, thank you. All right, now we get to add them up. So we're gonna add up 1, 2, 4, 5, 6, 7. Okay, 8, 10, 16, 17, 20, 25, 30. Check my math because I'm terrible at adding. There's a reason I don't teach elementary school. 10, 15, 20, 29, 23. Whoops, 33. What? No. Someone do this big row. I can't do it. This one, I can do the bottom row. It's only 2. 9, 11, 14, 18, 19, 23, 24, 27, 30. All right, someone help me with the middle row. 51. Thank you. Bless you. Okay. Isn't that interesting? Anyone want to share any observations before we flip? Anybody? So it got a little weird on the ends, but what are you noticing? All right, that's fine. You can hold your cards close to your vest for a minute. All right, we're going to construct a bar graph. Okay, we're going to do title and labels. All right, so what are we graphing down here? This is for our class data, the one that we just did in purple over here for the totals. Yeah, so this is going to be our number of heads. Okay, and then this will be our class frequency. Okay, so what are our options for a number of heads? We could have 0, we could have 1, we could have 2, 3, and 4. Okay, what was our highest frequency for any of our options? Looking at the class data, our totals. What? 51. Okay, so we need a scale that lets us get up to 51. So do I want to just count up to 20? No, that doesn't make any sense. Make sure you have room to go to 51. So I'm thinking we could count by kind of like tens. 10, 20, 30. Oops, I could do it bigger than that. 10, 20, 30, 40, 50. That looks pretty good. Okay, what do we get for 0? 7. So we want a cute little bar that goes up to 7. All right, what about for 1? How many times did we get 1? 30. So we want our little bar to go up to 30. Okay, what about 2? 51. Okay, that's kind of like a little Greek column. It got a little bit wider on the bottom. It's fine. It makes it look even higher. All right, how many times do we get 3? All right, and then 4. Okay, a little baby one. How would you describe this distribution? Oh, yeah, look at that. Oops. Okay. What do you think about this? What does that kind of look like? What? A bell. Okay, so what do you notice about the graph? Well, the distribution is roughly symmetric. It kind of looks like a bell shape. Anything else we want to say? So when you look at individual frequencies, like for mine was really lopsided towards not getting any heads, right? Right? And then, you know, some of these other ones were pretty symmetric, but like in the end, didn't it kind of even out? Like the more trials you do, the more this data is in theory going to approach like a symmetric distribution. It's kind of cool to think about. Okay. All right, suppose that we performed almost the same experiment, but we flipped a coin 6 times instead of 4 for each trial. Would you please draw a sketch of what the bar graph of the results would look like? So how many times could we possibly get heads if we were flipping 6 times instead of 4? 6. So instead of 0, 1, 2, 3, 4, we're going to have 0. Okay, would you please draw for me what you would expect that to look like? Did everybody get something that looks kind of similar to this? Okay, we will talk more about this later. Okay, we kicked all the kids out. We're just gonna finish this video because like we're already on a roll. Okay, but it's just gonna be me, like the kids are gone. So there's no one answering anymore. I'm just talking to myself. All right. So basically what we should have here is some, like the shape that looks like our one from above. We should have this pretty bell shape. Okay. All right. Oh, we gotta find the Galton board video. Okay, I gotta find that. Hold on a minute. Okay, we're gonna watch this video of this guy who's weirder than me. It's hard to do, but he does it.
About the Galton board. Invented, or at least named after Francis Galton, what we have is a bunch of pegs and a bunch of slots. Now when I turn this over, all of these balls, 3,000 of them, will fall through those pegs and they'll scatter randomly, in the sense that we don't know where each individual ball will go. But because there are so many of them, out of chaos comes order. Look at all that wonderful, wild randomness turning into pretty much the same exact shape every single time. A normal distribution. Let's begin by talking about the pegs. The pegs on my Galton board are arranged in a triangular pattern like this. We start with one peg. Below that peg in the second row, there are two pegs on either side. The third row contains pegs arranged like this, the fourth like this, and so on. Now it's because of this arrangement of pegs that the Galton board is sometimes called a quincunx. A quincunx is a pattern of 5 objects, a certain way of arranging them, where 4 of the objects are on the corners of a square and the 5th is in the middle. You're probably familiar with the quincunx if you've ever looked at a die before. Now anyway, when the balls fall through the machine, they first reach peg number 1 in the first row. And once they do that, they have a choice. Well, they don't really have a choice, but they will either go left or right. And because of the way the Galton board is designed, there's about a 50-50 chance that any given ball will go to the left or to the right. Once that's happened, they've reached the second row of pegs, where they will either go left or right, left or right. Now because at each peg, a left or right bounce is equally likely, in the long run, across a large number of trials, we expect balls whose complete paths contain about the same number of left and right turns to be the most common, which means we expect more balls to wind up pretty much right below where they started, and many fewer on the edges, which corresponds to having way more of one kind of bounce than the other. We don't know where any individual ball will wind up, but we can say something about how they will all behave. Now, the actual probability that an individual ball will fall into any one of these slots follows what is called a binomial distribution. But there's a nice thing in mathematics called the central limit theorem, which tells us that under a large number of trials with a large number of objects, like 3,000 balls, a binomial distribution approximates a normal distribution, which is what you see drawn here on the board. But this Galton board doesn't just demonstrate the central limit theorem. It's got a bunch of other cool features. For instance,
Okay, after that he goes beyond the scope of the class. If you're interested in watching the whole video, I will link it for you in our classroom. Okay, so that was our Galton board video. So we have, okay, when a histogram of a data distribution has a bell shape, the distribution can often be modeled by a normal curve, which is a bell-shaped continuous function. The properties of a normal curve make it a useful model for data distributions. In an approximately normal distribution, the percentages of data that fall within intervals determined by the mean and standard deviation are, okay, so this was on our notes in a slightly different way a couple days ago, but this middle bit is your mean. Remember that for a normal distribution, your mean, your median, and your mode are all in the same place. They're all in the middle. Now, if you take your mean and either add or subtract one standard deviation, that means you will have 68% of your data falling between within one standard deviation. So this is 68% of your values are within one standard deviation of the mean. Okay, look at the next one. Now, if you take your mean and you either add 2 standard deviations or subtract 2 standard deviations, then 95% of your values are going to fall within those 2 standard deviations of your mean. Okay, last but not least. Okay, here's your mean again. If you either add 3 standard deviations or subtract 3, then 99.7% of your data is going to fall within those 3 standard deviations of the mean. Okay, the percentages of the data corresponding to 1, 2, and 3 standard deviations in the normal curve are collectively referred to as the 68, 95, why does this say 6 and that says 7? All right, let me look it up, because they can't both be right, right? Okay, it's the 7 is right. This one's the typo. It's 99.7. Or the empirical rule. Using the normal curve as a model for data allows us to predict the likelihood of specific data values or intervals occurring. Now, when on the video we saw that one ball, like we had no idea where that one ball was going to end up, whether it was going to be in the middle or at the end, but with like all of the many thousands of balls that fell, we have a pretty good idea of the shape that they will fall into. Okay, so that is repeated again and again, time and time again through multiple trials. So we can use that to predict the likelihood that certain things will happen. Not like for sure, but good predictions. Okay. So there are certain phenomena that are naturally occurring and they fall into an approximately normal distribution. So one of them is heights of people in a population. So here we have a histogram, and it shows the distribution of Okay, well that says height and this says weight, but this also says weight, so I think that this might be a typo. I think heights also fall. I don't know. I think both happen. So this is baby birth weights in the United Kingdom. What do you notice about the histogram and its relationship to the normal curve drawn superimposed on it? So the shape of the histogram roughly corresponds to the normal distribution. I ran out of room. Yikes. Okay, so in our data, the mean weight of a newborn baby is 3.39 kilograms. Okay, 3.39. Like maybe here-ish. So that's our X bar. Okay, and the standard deviation is 0.55 kilograms. So, if we took that 3.39 and added 0.55, we would get 3.94. Oof, I wanted it to be pink. What did I say, 3.94? So like about there. Ish. And then if we subtracted the 0.55, we would get, this is plus 1 standard deviation, and it is at 3.94. So we took our mean, we added 1 standard deviation, which was plus 0.55, and we got this amount. Now what if we took our mean and subtracted the 0.55? So this would be minus 1 standard deviation. We get 2.84. Like about there. We would get 2.84. Now, because this distribution is kind of like a normal distribution, it roughly corresponds to a normal distribution, we can expect that in this region between, within 1 standard deviation of our mean, 68% of our babies fall in that interval. Okay? Now, it doesn't say what percentage though. It says how many newborns. They want the number. So we need to know, well, how many babies were in this study? And that's right here. There are 3,226 total babies. Okay, 68% of those we would expect to find within 1 standard deviation. So all I have to do is do, where's my calculator? 0.68 times, how many babies? 3,226. 3,226. All right, I'm getting 2,193.68 babies. 2,193.68 babies. Actually, these are baby weights, right? Within how many are in? 1 standard deviation of the mean. All right. So we use the empirical rule saying 68% of our data is likely to be between, well, within 1 standard deviation of our mean. And we use that 68% and we find 68% of our total baby weights. And it tells us how many babies were in the middle. Okay. About how many newborns from the study would you expect to have birth weights within 2 standard deviations of the mean? So this time, right here's our mean. Okay, let me look at my old picture. Under 4. Okay, we had 1 standard deviation was here. Ooh. Another one was like here. Okay, now if this was plus 1 standard deviation and this was minus a standard deviation. Now if I go out again, this would be plus 2 standard deviations, right? Oops, that's not plus, that's minus points. Okay? And then I could go out again, really. Okay. So, within 2 standard deviations of the mean, using our empirical rule, that is 95% of our data, our babies, our baby weights. So we would do 0.95 times our, how many babies? Is it 3226? 3226 over 3226. So 0.95 times 3226 equals 3,064.7 babies. Okay, about how many newborns from the study would you expect to have birth weights within 3 standard deviations? So my 3 standard deviations, this is, according to my empirical rule, 99.7, not 0.6, sorry about the typo. So I'm doing 0.997 times my total babies, 3,226. That is 3,216.322 babies. Okay, so, like that's most of the babies, right? We've only got 3,226 babies, so like only 10 of them are outside of 3 standard deviations. It's most of our babies. If these data are an indication of birth weights in general, would you expect many newborns to have a birth weight of 5.55 kilograms or 12 pounds? Well, let's find that on here. 5.55, that would be here. So that is outside of our 3 standard deviations. So it's extremely unlikely that a baby would have that weight. No, because .5 kilograms is more than 3 standard deviations above our mean. Okay, so let's think about this. If 99.7% of our data falls within 3 standard deviations, then how much of our data is left to be outside of that? So we've got our 100% of our data, and what if we subtracted the 99.7%? That just leaves us with 3% left. Sorry, that's 0.3, Moinitz. That's 0.3% left. Okay, now that's 0.3 for the top and the bottom, for the high end and the low end. Together is 3%. So if we're talking about like half of the 0.3 goes on top and half of the 0.3 goes on the bottom, we have to divide this in half. So it's 0.15%. So what we're saying is within 3 standard deviations, we would have 99.7%. Right? Outside is 3%, 0.3%. I keep doing it. Gosh darn it. So that would be 1.15% down here, and then another 0.15% down here. Because the 0.3 has to be split. So, I'm rambling. You should have been in class, and then you wouldn't have had to watch all this rambling. Okay, so therefore, there only 0.15% of babies would be above 3 standard deviations from the mean. So if we did 0.15. Okay, so the 0.15 is a percent. So if I converted that into a decimal, that would be 0.15 divided by 100. That was 1,000. That's what we're looking at. And then multiply that by our babies. 3, 2, 2, 6. I mean, we're looking at between 4 and 5 babies that are that big. That's not very many. All right, I think I've harped on that long enough. That was fun. Okay, so let's talk about gorillas. The lifespans of gorillas in a particular nature preserve are normally distributed. Good to know. That means that we can use the empirical rule. The average gorilla lives 20.8 years. The standard deviation is 3.1 years. We have 400 gorillas. We're going to use our empirical rule to estimate. Oh my gosh, they're doing something noisy in the hall. I'm going to pause this. I'll be right back. Okay, so this is what we're going to do. We're going to make a little number line. Okay, and then I want you to give me like a bell shape. Here, let's put our mean in the middle first. Okay. So I want you to give me a nice bell. We're going to kind of like vertically compress this a little bit so that we have room to write. So our mean is 20.8. So that's this right here. That is our X bar. All right. Standard deviation is 3.1 years. So I'm doing 20.8 plus 3.1. And I got 23.9. So plus 1 standard deviation is 23.9. This is plus 1 standard deviation. Now if I subtract 20.8 minus 3.1, I'm getting 17.7. So this is minus 1 standard deviation, and it is 17.7. All right, let's keep going. Now if I add another standard deviation to the 23.9, so 23.9 plus 3.1, I get 27. So this is plus 2 standard deviations. So I've added 3.1 twice, and I'm getting 27. Let's just keep adding because it's easier than switching back and forth. So I'm going to add 3.1 again, and I got 30.1. Okay, I tried to get these kind of even, but it's looking a little bit lopsided. So that is user error, not. Okay. So now I'm doing 17.7, and I'm subtracting 3.1 to get my minus 2 standard deviations. So this is minus 2 standard deviations, and I'm getting 14.6. Now I'm going to subtract 3.1 again to get my minus 3. Minus 3 is 11.5. Okay. So our empirical rule says that from within 1 standard deviation, this is 68% of our data. Within 2 standard deviations, that's 95%. Within 3 standard deviations, whoops, too far. That is 99.7% of our data falls within that range. So we want to know what percentage of gorillas will live 17.7 to 23.9 years. Well, 17.7 to 23.9, that's just within 1 standard deviation of our mean. So we can expect that by the empirical rule, that would be 68% of our gorillas. If they asked us the number of gorillas, we would just do 0.68 times our 400 gorillas. See, we got 400. 0.68 times 400. 272 gorillas. Okay, it does ask us the percent though, so we could have just stopped there. That was the right answer. All right, B, how many gorillas will live from 14.6 to 27 years? Okay, well, that corresponds to within 2 standard deviations from our mean. So that is 95% of our gorillas. Okay, this is plus or minus 2 standard deviations. So we're going to do 0.95 times our 400 gorillas. Because this time it's not asking us just for the percent, it's asking us how many actual gorillas. We want a number, not a percentage. 0.95 times 400, 380. Okay, what percentage of gorillas will live 20.8 to 23.9 years? Well, guys, that's only this bit. So that's not our entire 68%. That's only half of 68% of our gorillas. So we're taking our 68% and we're chopping it in half. So we want 34% of our gorillas. That's a G. Okay. How many gorillas will live more than 27 years? This is where it gets exciting. More than 27. Okay, it's been over a year since I've done this. Let me think about the best way to explain it. Give me a second. All right, I got it. I had to draw a little picture for us. Okay. So in order to figure out how many of the gorillas are going to live more than 27 years, we first have to figure out kind of like how many are going to be between 14.6 and 27. So the 14.6 and the 27, that is plus or minus 2 standard deviations. Okay, so that's 95% of our data. Okay, the remaining 5% of our data is on the ends. Okay, so what's happening is that this bit and this bit add up together to be 5%, meaning there's 2.5% at the bottom and 2.5% at the top. So if I only care about the more than 2.7 and I don't care at all about under 14.6, I get to ignore these gorillas down here. So I don't want those ones here. I don't want the 95% in the middle. I only want the 2.5% on the top end. So I only care about this 2.5% who are going to live more than 27 years, likely to live. So I'm going to say, turn that into a decimal. So it's 0.025, right? Right? It's a decimal times my 400 gorillas. I don't know what it is yet. I have to put it in the calculator. All right, I'm getting 10 gorillas. All right, how many more of these gorilla questions do we have? Geez Louise. How many gorillas are going to live less than 23.9? Okay, so 23.9 is plus 1 standard deviation. Oh, this is a fun one. All right, let me draw another picture and then come back to you, okay? All right, here's my picture. So my mean is here, there's my x-bar, and then 23.9 is my +1 standard deviation. 23.9, that's my +1 standard deviation. All right, so because my mean, my median, and my mode are in one place, right here is 50% of my data. Hold on, let me write that nice and big. Make that a little bit bigger. This down here is 50% of my data. And then we figured out from the problem above that between my x-bar and my +1 standard deviation in this region is half of 68. This, remember, was 34% of our gorillas. So we have to take the bottom 50% and then add to that half of my 68%, which is the 34. So call it, oh my gosh, 84%? 84% of gorillas. Okay, but guess what? We're not done yet because it doesn't ask us what percent, it asks us how many. So I still have to convert that into a decimal and multiply by 400, and I'm running out of room. That's fine. So it's 0.84 times my 400 gorillas. I don't know. I just did 4,000. I'm getting 336 gorillas. All right, how many gorillas are going to live from 14.6 to 23.9? Oh, these are real exciting. That was mean. That was real mean. All right. Let me think of how best to explain this and draw a picture. Okay, so I redrew my picture because it was getting kind of wild on my other picture. This is +1 standard deviation. Here's +2 standard deviations. Here's +3 standard deviations. Here's -1 standard deviation, -2 standard deviation, and -3 standard deviations. Okay, so the 14.6 is here. And the 23.9 was +1. So we want to know how many of our gorillas are in this region. So it would be really helpful if we know, for example, that this is 95%. And this is 68%. The question is, can we find out what is here and what is here? So if I did my 95% and subtracted my 68%, I would get, you should do this too, 95 minus 68, 27%. Okay, now that 27% is split evenly here and here. So I'm going to have to divide that in half, giving me 13.5% here and 13.5% there. So if we want to know what is from the 14.6 to the 23.9, it's going to be my 95 minus this 13.5. Or you can think of it as a 13.5 and a 68%. You should get the same thing either way. So I can either do 95 minus 13.5, or I can do 68 plus 13.5%. And you should get, excuse me, 81.5% of our data is between 2 standard deviations below and 1 above. So we still need to know how many that is. So I'm going to take 0.815 times my 400 gorillas. And I'm getting 326 gorillas. Whew, yeehaw. Okay, so in addition to your empirical rule, there are some useful percentages that if you can memorize them, they will help you out a lot. So the first two are going to be pretty obvious, because we just take our 68% and we chop it in half. So on this side, between 1 standard deviation below the mean and the mean itself, we have 34%, and then we also have 34% here. Okay? In between -2 and -1 standard deviation is 13.5, and then the same on the right. Between +1 and +2, I have 13.5. All right, I'm gonna boop, 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 boop. All right, let's just keep going. I mean, shoot, we're already there. Let's just do it. I need some white down here because I ran out of room. Ran out of room. Okay. So, from woo. Okay, from here to here, we got 99.7%. Okay, so if I subtract the 95 from the 99.7, which I believe that we have already done, I just did times. I'm getting tired. Maybe we haven't done it. I'm getting I'm getting 4.7%. Okay, now if I take that 4.7% and I chop it between these two ends, I'm getting 2.35%. So this right here is 2.35%, and this is 2.35%. Oh, it's the very ends that we already did. So we did the 100 minus the 99.7 and we got 0.3. Okay, so the very, very, very tail ends. This is the 0.15%. And the 0.1, whoop, fun with decimal places, 0.15%. Okay, that was a lot. I need a coffee. Or a lobotomy.